6.2, Integration by Substitution, Part B. So here are some new formulas for integrals. On the left, we have natural log, and on the right, we have the exponential function e. They're pretty straightforward. Anytime that we have an integral where whatever is in the problem can be reduced basically to a fraction of 1 over something, it's going to be natural log. If you've noticed, we've never encountered a problem like this. And the reason for that is because the rule is you add an exponent and divide by the new exponent. If I were to add an exponent to -1, that would be -1 plus 1, so I would end up with x equals x to the 0 power. So whenever you end up with x to the 0 power, this doesn't work. And the integral is natural log of whatever x or u. E to the u has always been simple. I mean, well, yeah, e to the x integral is just e to the x. U can be substituted in for like a really long function or something. The integral is still e to the u, but most of the time we'll compensate. For example, du here would be 2 dx. There's no 2, so then I would divide by 2, and then this would be 1/2 in the front, etc. Okay, so that's what we're doing. Okay, so here I have 2 over x. So I'm going to simplify this. I'm going to write it like this, because I want to show you that this is just a multiple, a scalar. I'm going to pull it up to the front. So now I have 2, and then I'm integrating 1 over x dx. And 1 over x is x to the -1 power, and whenever that happens, the integral is the natural log of my x. And then, of course, since I don't have any limits, plus c. Now, it is the absolute value. There are some times that you don't have to worry about the absolute value. For example, if it had been x squared, you know there's no way this can be negative. So you don't have to write the absolute value. But if there is a potential negative value in the equation or wherever, you got to use the absolute value. Example 2. Okay, so what I want to do now is I want to use substitution. So we're going to call this u. See, in the previous example, it was just a plain old x. But here it's a little more complicated. So 4x minus 1. So du is 4 dx. And just like before, I want you to find these pieces. Oops. 4. Okay, so the dx is here. The 4 is MIA. So then that's when I have to compensate for it. And I'm just going to divide both sides by 4. So now, whenever I do replace the dx with du, it's also going to have a 1/4. Okay, so replace. So the 1 over the bottom part here is u, and then the dx is going to be replaced by du and 1/4. And from the last lesson, hopefully, you recall that I prefer to pull out the multiples, the numbers that we're just multiplying by. Another word for it would be a scalar. Scalar is a good name for multiples. Okay, so now I have this integral, and this is what I'm integrating. So the 1/4 stays. 1 over u becomes the natural log of the absolute value of u plus c. And then, of course, u didn't really exist to begin with. We're using that to make this easier to do. So 1/4 natural log, and then plug in 4x minus 1 plus c. Example 3. Okay, so again, which part of this looks like the derivative of the other? And x squared plus 1 looks like the original equation, where du kind of looks like the derivative. I'm deriving u. It is 2x dx. Now in the problem above, dx is dx. This part right here is this part right here. This is this. The only thing missing is the 2. So divide by 2, divide by 2. So when I do replace stuff in this function or an integral, dx and x are going to be replaced by 1/2 du. So dx is now du. The x goes away. I also need to add a 1/2. I'm going to put that outside. So that just leaves me a 1 as a placeholder, right? And then the bottom part, x squared plus 1, that's the u. So integrate this. So the integral of 1 over u is natural log of u plus c. All right. U didn't actually ever exist. Plug in x squared plus 1. And then here is my example where the absolute value is not necessary. There is no x value on the planet. I can plug into x. Real numbers here, people. Real numbers. That I could plug in for x that will make x squared plus 1 negative. Nothing. So the absolute values are obsolete. I don't really need them. And there you go. All right, example 4. I can see. Okay, example 4. So again, which part looks like the derivative and which part looks like the original function? So the denominator is x squared plus 2x. Derive that is 2x plus 2 dx. Now here, this is a perfect example where the derivative doesn't look exactly like the part of the integral that should be the derivative. But with a little bit of algebraic manipulation, we can make this happen. I see a factor of 2. So now I'm going to make this x plus 1. And so, okay, so the dx, x plus 1, x plus 1. So there is no 2. So divide by 2, and there's the 1/2. The denominator is right here. So replace everything. Oh, let me move that over. Okay, so the x plus 1 and the dx. These go away and they get replaced by this. I put the 1/2 in the front. Here's the du. And then 1 on top of the in the numerator to hold the placeholder. And then the bottom is going to become u. So integrate. Get 1/2. 1 over u is the natural log of the absolute value of u plus c. Replace u, or return what was originally there. And that was x squared plus 2x. I can't see. Plus c. Now, here, I do have an x squared plus c. But there are values where I could plug them in here, and it could mess it up and make a negative, right? So like -1, or let's see, something good. -4. If I plug it in, I get 16 plus or minus 8. Let's see. Okay, so that's not negative. -1. If I plug in -1, I get 1 plus 2 times -1 is -2. Oh, look at that. Okay, so that's the absolute value. And if you're wondering why I can't have my values be negative, you might want to plug in natural log into the calculator and put a negative number in it and see what happens. Another way to think about this is the graph of natural log looks like this. There are no negative values. Okay. Example, oh no, try it. So I'm going to pause it, and then I want you to try this. All right, there you go. There's the answer. There's all the work. Hopefully you got the same results. Example 5. Okay, so now we're going to lean off of natural log, and now we're going to work with e to the x. Okay, so this is still substitution. I need you to look at this and figure out what part is the exponent part of the e, right? Which is not a big deal. Duh, it's right there. And then, so that's going to be your u. And then once you have your u, just like before, you would derive it. And so you start finding the pieces. Dx to dx. This x right here is this x right here. Oh, MG, I don't have the -2. So then you would compensate for that. Now, if you look at the equation or the function, the integral, sorry, it's that 5. I don't have any way to account for that 5. So the easiest way to think of it is just to basically, okay, that is being multiplied, so that could just go outside, right? And so then this is now basically everything I had over here. Here's my x, here's my u, and then my dx. So my x and my dx are going to be replaced by, so my x and my dx are going to be replaced by -1/2 du. But oh yeah, Mrs. Ronan likes to put the numbers like -1/2. Anything I'm multiplying, I just like to put them outside. Makes it easier to work with the integral itself. So there's the 1/2. Here's the du. And then it's going to be e to the u. All right, so I have -5/2 out here. And then e to the u. So the integral of e to the u is e to the u. And then plus c. So then I would go ahead and, since u was just something that I used to be able to integrate easier, I would replace it or put back in what it actually originally was. And u was -x². And there you go. Don't forget the plus c. Okay, so here I have another try it. I'm going to pause. I want you to pause. Try it. It's going to be written out for you. There you go. Now, obviously, a good technique to check to make sure, OMG, did I do this right, would be to just go ahead and derive to check, right? So if I take my answer here and I derive it, obviously the plus c is a constant, so it becomes 0. But the way to, what do you call it? The way to derive e to the x is basically you leave e to the x alone, and then you multiply by the derivative of the exponent. So leave e to the x alone, and then multiply by the derivative of the exponent. The derivative of the exponent is 3, right? Because 3x plus 1, the derivative of that is 3. And then that's how the 1/3 disappears because of the 3. And so I have e to the 3x plus 1 power. And that is the integral I started with. Okay, so again, figure out your exponent here, which is easy, really. Finding the exponent isn't hard. I mean, there's an e there. So that's your u. And then du is going to be the derivative of that. So derive cosine, and you get negative sine x dx. So then look for these pieces. dx, dx. Sine x is right here. That negative, however, is not. So compensate. Divide by -1/2. Divide by -1/2. I'm sorry. Oh my God. Divide by -1. Divide by -1. Also multiply by -1. That would do the same thing. So basically, I'm going to have a negative du. And it works the same way as a 1/2 or a 1/5 or 5/2, whatever. It would work the same way. I would put that one or that negative out in the front, get it out of my way, so I can make sure that I don't get it all mixed in. So here's my negative. And then dx and sine x are going to be replaced by this negative right here and du. And then e is now e to the u. So integrate this. So negative e to the u plus c. And then, of course, replace the u. So negative e, u was a cosine x plus c. And that takes care of that. Example 7. Okay, so here we have limits. So this is the first example that we actually have upper and lower limits. Okay, the previous 6, no limits. So no plus c anymore. We're actually going to evaluate. So here's my u, So u is negative x. Du is negative 1 dx. Figure out what is what, replace the stuff. And remember I said that I like leaving it all in terms of u. You're free to do that. You don't have to. And I will do it just because I said that I do prefer it for all the other problems, so I might as well be consistent. Okay, so this is now e to the u. And then the du and the dx, they're not quite right. Here's dx, but that negative 1 is nowhere to be found. So I'm just going to add a negative here, right? And basically that goes away. So I have negative e to the u du. Finish integrating that. And I have negative e to the u. No plus c because I'm going to evaluate. And again, I like just leaving it all with u's. That way I don't have to go back and forth. So in order to do that, I'm going to plug in my original limits, the 1 and the 0. So this right here, and then this right here, right? So plug in the 1 into u. So that's negative 1, right? And then plug in the 0. So it's negative 0, which is 0. So now my new limits are negative 1 and 0. Recall that I realized the negative 1 is a smaller number, but it's on top. But I got negative 1 when I plugged in the original upper limit. So it stays in the upper limit spot. Okay, so I'm going to move this out of the way if I can. Oh, let me move it some other way. Okay, so now I have negative e to the negative 1 power minus negative e to the 0 power. You gotta like 0 power because that makes everything 1. And then this is negative e. You know what? I'm gonna write it as a fraction. Why not? So 1 over e, and it's negative. And you could leave it like this. This is okay. You could also pop it in the calculator, and you could also write it as a I'm sorry. You could pop it in the calculator and write it as a decimal, or leave it written like that. No biggie. Oh, look what I did. Negative, negative. Okay, so rewritten like this is perfectly fine, or written like this, not rewritten. You could, however, write it like this if you don't like the negative in the front. And if a multiple choice answer is rewritten like this, it's no big deal, right? They didn't change anything. They just put the 1 in the front and then minus 1 over 8. But if you do pop it into the calculator, let's see, what do we get? We get 0.632. And remember, in this class, you round everything to 3 decimal places. So whichever. They're both good answers. You're not always required to simplify. Okay, example 8. So figure out what is what. See here, when you see a fraction, your first thought should be maybe it's natural log. So what part of this is the derivative and what part isn't? The denominator is going to be u. And then du, the derivative of that is just e to the x dx. So looking up over here, okay, this is slightly different, right? Because we are dealing with natural log here. Because it's not just e to the x. It's in fraction form, so that's kind of like a clue that we're dealing with natural log. So dx, e to the x, that's accounted for. The u is this part right there. I like working with just u, so I'm going to go ahead and plug in my limits into u. So my upper limit is 1 and my lower limit is 0. And so I get 1 plus e to the 1, which is just 1 plus e. And then I get 1 plus e to the 0, which again, e to the 0 power is 1, so 1 plus 1, so that's 2. So these are my new limits now. Yes, 1 plus e is going to be a limit, no biggie. So c's get replaced by just du, and then the denominator is going to be u. So integrate this. And then, oh, I almost forgot my limits, my new limits. 2 and what's the 1 plus e. Okay, so integrate this. 1 over u becomes a natural log of u plus c, but I have limits, so we're going to evaluate it from 1 plus e and to 2, or 2 from 1 plus e, or from 2 to 1 plus e. Okay, I can't talk. Okay, so plug in natural log of 1 plus e. Oops. Natural log of 1 plus e. There we go. Minus natural log of 2. Now, the natural log of 1 plus e, that could be plugged into the calculator. All right, so I plugged those things into the calculator. Natural log of 1 plus e is 1.313 minus 0.693, which is the natural log of 2. And then, so I got 0.620. All right. To try it, I'm going to pause. I'll show the work, and we'll be done. All right, here it is. I figured out what u would be, and it would be the stuff inside the parentheses near the cosine. So it's cosine u. I figured out what part was the du. I got my new limits for u. So I integrated using u, and I stayed with u. And then I plugged in the 1 for sine of u. So sine of 1 minus sine of 1 over e. And then popped in the calculator, and I got a decimal. Okay. Homework, be ready for class.